All right, I want to build a Taylor polynomial for the function f of x is equal to 1 over 1 minus x. And I'm going to tell you that I just did this and I actually made a mistake on it, and then I had to come back to it. So I may delete the old video, or I may just leave it up there to show that I make mistakes too. But I guess you already knew that, so maybe I'll just leave it up there because I'm lazy, and then I'll think of an excuse for me to leave it up there that makes me come off good. But so to construct the Taylor polynomial, what I need to do is start taking the derivatives. By the way, I am going to center it at 0. F of 0 is 1. And that makes it a Maclaurin. A Maclaurin and a Taylor is like a Kleenex and a tissue. A Kleenex is a type of tissue, but not every tissue is a Kleenex. But sometimes we forget and use them interchangeably. A Maclaurin is a type of Taylor series that's centered at 0. So the first derivative, when you think of what this is going to be 1 minus x to the negative 2. And then I'm going to have to multiply this by a negative, because if I do 1 minus x to the negative 1, then it's negative 1 times 1 minus x to the negative 2 times another negative 1 because of the chain rule. So what happened? The two negatives cancel. So then if I take the second derivative, I'm going to get negative 2 times 1 minus x to the negative 3, and then I'm going to times it by another negative 1, and my negatives are going to cancel. So f prime of 0 is 1. The second derivative at 0 is 2. The third derivative is going to be 6 times 1 minus x to the negative 4th. The third derivative at 0 would be 6. If I think of the nth term, the general term, at x, I'm going to get, what am I going to have? I'm going to n factorial times 1 minus x to the negative n plus 1. And if I think of fn of 0, I'm going to get, let's see, n factorial. And then if I'm going to construct a Taylor polynomial, well, let's go back to the mystery function game. Let's say I'm constructing a mystery function where I know that g of 0 is 3, the first derivative at 0 is 8, the second derivative at 0 is 42, and the third derivative at 0 is 54. What's my approximation going to be? Well, you might think it's going to be 3 plus 8x plus 42x squared plus, that's a 54x cubed. And you might think that, and then you might think, well, let me just test it to make sure that that's right. What's a prime of 0 going to be? Well, I'm going to take the derivative, and that's going to give me 8. And then I'm going to plug in 0, and the terms that still have an x in them are going to cancel out, so that gives me 0. I'm going to take the second derivative, and these two things are going to have canceled by the time I get to the second derivative, but this is now going to be not 42, it's going to be 84, okay? And if I take the third derivative at 0, by the time I get there, these first three terms will have canceled, but then this isn't going to be 54, it's going to be 3 times 2 times 54. Okay, so that's a problem, but it's not a problem that has a difficult solution. We just have to offset it with some kind of an inverse, which is why we put the 2 factorial here, even though not 2 factorial and 2 are the same thing. It just gets used to the pattern. We put the 3 factorial there. So this is the point when some people forget where that factorial comes from when we're constructing the Taylor polynomial. That's where it comes from. And so then what is my function going to look like? Let's call it p of x is going to equal 1 plus 1x plus 2x squared over 2 factorial plus 3, let's say 6x cubed over 3 factorial plus dot, 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 n factorial x to the n over n factorial. Well, I'm sure you can look at this and say it's easier to just say 1 plus x squared plus x cubed plus x to the fourth plus dot, 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 x to the n. And you can probably also say that the easier way to do this would be to say this is the sum as n goes from 0 to infinity of x to the n. And now what you should know is that you can use substitution. So if I say, what does 1 over 1 minus x squared equal? Well, I could say this is the sum as n goes from 0 to infinity of x squared to the n. What does 1 over 1 plus x equal? Well, this is 1 over 1 minus negative x. So this could be the sum as n goes from 0 to infinity. And now I'm just plugging negative x in for that. So this would be negative x raised to the n. And that's called substitution, which is a word that you've seen used plenty of times before. But it can be used for Taylor polynomials, and it's actually it's actually really effective and helpful. You may also think, this is cool. What does it mean? Well, it means that, like, if I'm to look at these things on a graph, it means that, well, here's 1 over 1 minus x, right? It's a hyperbola. It's got an asymptote. And it means I could approximate it using this thing. But it also is like, you're also kind of like, well, it gets better and better the higher I go up. The ladder A represents the number of terms I include. But it's also not doing that well outside of a certain, what is that certain range that x equals 1 and x equals negative 1. My thing's going a little bit slow, but let's make this black and let's make it dashed and let's make this one dotted too. And it looks like within this range from negative 1 to 1, right, we're doing a pretty good job of predicting. But outside of that range from negative 1 to 1, it's not doing a very good job of predicting. Well, I wonder why that could be. Well, do you remember back when we talked about intervals of convergence? This is the power series. Over what interval does it converge? Well, if you think of it, when x is between, this is a geometric series. When does a geometric series converge? And right now in my head, I'm picturing like fireworks and explosions going off in your head when you realize that this will only converge as an infinite series when x is between negative 1 is less than x is less than 1. And so now, perhaps in a roundabout fashion, we've connected intervals of convergence back to Taylor series approximations, and we've shown substitution. And it's a lot to wrap your head around, but now you can start to see how these things are a little bit connected.